We are at another new data structure, stacks. It's going to be fun. Stacks are an abstract data type, this ADT we're going to start seeing a lot of. So what is an abstract data type? To answer, this is best really given by stating what is the negative. What is not an abstract data type, at least in Java? An example would be an int value. An int is a primitive data type. It's built into the core feature set of Java. Double is a primitive data type built into the core feature set of the Java language. There's other primitives that you can think of. There's many other data types that are these not an abstract data type. And think of that meaning of the word abstract, right? So again, what is an abstract data type? I'm going to say it's something that's not actually built into the core feature set of Java. And notice I say, well, for our purposes, it isn't. And I'll explain more about that in just a moment. But an abstract data type is something that we're going to build. We're going to actually define it and build it from the ground up. And usually abstract data types are defined in terms of their behavior rather than its implemented representation. I often quote this definition from Wikipedia because it's concise and it has good value. An abstract data type is defined indirectly only based on the operations that may be performed on it, meaning based off of its behavior. So stacks are an abstract data type. Now here's a question. I said on the last slide, for our purposes, it's not built into the language. But here's the question. Does this mean that stacks are not built into Java? I say yes and no. You could say that stacks were not built into maybe the original feature set of Java when Java first came out, right? But however, over time, we have so many new libraries, so many classes that were added to Java. It's now a very rich language. So you can be sure that stacks are part of Java in the same way that linked lists are part of Java. Yet we've had videos where we build linked lists from the ground up because this is something you want to be able to do as a computer scientist, as a learner of computer science and data structures. You want to actually build these data structures on your own, learn them from the inside out, create them, and then sure, learn how you can also use those given data structures within the API provided to you by a given language such as Java. So we can absolutely say that stacks are 100% part of Java. There is a class called stack. However, for the purpose of this course and these videos, we want to build our own stack. So we're just going to assume for now there is no built-in stack in Java, and we're going to create it ourselves. So we need to define what is the behavior of a stack, or we could say more simply, what is a stack? It's a data structure that stores information in the form of a stack, and it consists of a variable number of homogeneous elements, however you like to pronounce that, elements of the same type. What is the access policy of a stack? The access policy is quite straightforward. The first element to be removed from a stack is the last element that was placed into the stack. Think of a cafeteria. Think of a buffet restaurant. We have that huge stack of plates that is super heavy and it's almost empty and you're trying to reach in to get that next plate and a worker comes out with like maybe 30 or 40 of these very heavy like porcelain plates and drops them in. Well, the first plate that was actually put into that stack is at the very bottom. So it's going to be one of the last plates that are removed from the stack. But the last plate that was inserted into that stack, in fact, is going to be the first plate that was removed. So the access policy is known as LIFO, last in, first out. The last element that was inserted into the stack is, in fact, the first element that we remove from that stack. Once again, the example being that of cafeteria trays. New clean trays are added to the top of the stack, and also we remove trays from that top of the stack. So the last tray in is in fact the first tray taken out. What are the operations that we can perform on our stack? There's famous universal operations that are used everywhere in the world on stacks. What are they? We have push and we have pop. What is push? Push, we're now adding a new element at the top of the stack. Pop, we are popping off or removing an element from the top of the stack. Another important tidbit I say here, the end of the stack where pushes and pops occur, you may have just heard me, I said from the top of the stack. We don't call it the front of the stack like a front of a list because a stack is normally viewed what? Vertically, right? So the end where we're performing the pushes and the pops is the top of the stack. What is a push operation? This is one of the most enlightening slides ever that is fully sarcastic, but yet I've kept it here because it's almost just so humorous how silly the slide is. Here we have a stack. Clearly 24 is at the top of the stack, and we would like to now push element 6 onto the stack. That's the result. Not much to say there. I hope everyone is okay with that. If we're not, I don't know how else to explain that. We are adding 6 to the top of the stack. Done. And now notice that top, which you're going to see really is going to be a variable, instead of pointing to 24, now top is pointing to the value or the location where the 6 is found, representing that is where the new top is at. What is a pop operation? A pop operation is where we would like to remove the element at the top of the stack. Here top was pointing to 6. If we want to perform a pop, what we need to do is remove that element 6 and send it off. Now you notice here, it's still kind of, it's like grayed out, or you see it in a different color, indicating it's not really part of the stack anymore. Notice that top is in fact pointing to 24, but depending on your implementation, that value 6 may still be in the data structure, and some people are like, oh no, I don't like that. I want to physically remove the 6. Well, depends on your implementation, you may not need to, right? Because as long as we change where top points to, the very next push will get pushed on top of where that 6 was, effectively overriding the value there. But we'll get to the implementations in just a bit. Other operations is empty. To check whether or not the stack is empty, this is usually implemented as a Boolean, returning true if there are no items in the stack. We have is full, also a Boolean, simply returning true if there's no more space in the stack. We say here, in theory, a stack should never become full, but in practice, it could become full based off of your implementation. The actual implementations may have limits on how many values can be stored in the stack. What is the top? Top is actually a method or a function that we can write for our stack. It's an operation. What does top do? It simply returns the value at the top of the stack, but it does not actually remove it. So distinguish between the method or the function or the operation called top and the top of the stack. The top of the stack is just the location where that uppermost value is, but the operation called top returns the value that is at the top without actually removing it. So you have the distinction between top now versus pop. Pop removes and returns the value, whereas top does not remove the value, but it does return the value. Some textbooks, some educators, instead of calling it top, they'll call it peek. Like we're trying to peek at something. Ooh, what's at the top? We're looking, and they call it a peek operation because we're not actually removing, we're merely looking at it. Maybe other places would call it look. It depends on the language, depends on the implementation, but you get the idea. So all of these operations, they access the stack, but they don't modify the stack. The ones that we just showed you, is full, is empty, top, they're merely accessing the stack. Also important to note is that a push can only be done if the stack is not full, right? Because if the stack is full, clearly you can't push on any more elements. A pop can only be done if the stack is not empty, right? If the stack is empty, clearly we can't pop and try to get an element from the stack. What we want to do is we want to write our own custom stack class, which we're going to do. You're going to see at the end of this video, we're going to have covered 2 different implementations from the ground up of our own stack class. But before we do that, I said we're going to assume that Java doesn't even have a stack class for most of this video. But first, let's go ahead and show you the one that's built into the Java API. Here's how you would create a stack of integer objects. Check it out. Stack integer, I call it S for stack, equals new stack. Kind of like array list integer, AL equals new array list. or linked list integer LL equals new linked list, right? Here, it's just you're changing the name of the data structure or the name of the class. In this case, it's stack. So we're creating a stack of integers. But now instead of add or get, these are the methods for an array list or a linked list, now we're going to be using push and pop. So here, I've created a new stack of integers. I push 5. I push 8. I pop and I print that result. Then I push 2 and 5. Then I pop 3 more times, each time printing the result. And then I'm going to push 1, and then we're going to pop and print that result one more time. So what I'd like to do is come over to the trusty tablet and now draw this one out. So first of all, I'm going to make a new stack. I draw it here as an actual stack. I'm going to put some placeholders in here. And what does it say? It says that we're going to actually push a 5. So we push the 5. What's the next line of code right here? What does it say? It says push an 8. So we push an 8. So now we have 2 values in that stack, the 5 and the 8. Now it says pop and then print the result we're popping. So we're going to pop a 5. We're going to pop. What does pop do? Pop removes the top item from the stack, which is this 8 right here. I'm just going to scratch it out. I'm not even going to remove it. I'm just going to scratch it. And we're going to now print it. So we print the 8. We call this output. So we're going to print the 8. And then what comes next? Push a 2. Notice the 2 comes at that same exact spot. So you can say that right here, we're currently at the top of the stack, right? So now we want to push the 5. Well, when we push this 5 right here, it's a new 5, right? So when we push that 5, we push it right here, and now top is pointing to here, and we need to change this. So now what do? It says we're going to pop 3 times, and each time we're going to print. So we're going to pop this 5. Let me scratch it out. We're going to pop it, and we're going to print it. I'm going to put commas here. Then we're going to pop the 2, and we're going to print it. And then we're going to pop this, and we're going to print it. And so right now, in fact, top does not even refer to here. Just think of these as your indices, 0, 1, 2, 3, 4. Top is not pointing to 0, because if top were pointing to 0, that would indicate there's a value at index 0. So currently, what actually happens is top, I'll draw it this way, top is really a variable, depending on your implementation, but let's pretend we have an array implementation. And currently, top is actually what is stored inside that variable? A -1, which is how we can indicate there's no values in our stack. Now we are here. We need to push a 1. So let's push a 1 into the stack. And then finally, we do this operation, which is pop. We remove that 1, we pop it off, and we print it. And that is just one example of using a stack in Java, using the push operation, using the pop operation, printing some output. Let's take a look at another example now. What is the output of the following? So check this out. We have another stack of integers. Now we have a for loop. How many times is that loop looping? From 0 to less than 10, so 10 times. Each time we're going to push into the stack that value I. So we're going to push 10 times. Then we're going to do 3 pops, and then we're going to do a peek. So let's actually trace through this one again. So at the beginning, again, top is -1. I need to actually do 10 pushes. So I'm going to start by pushing I is 0. Then I becomes 1. We're going to push 1, then 2, then 3, then 4, 5, 6, 7, 8, 9. Right? We're going to do 10 of them from 0 to less than 10. So 0 to 9, we push those values. Then we pop 3 times. It doesn't say pop, then print that value. It just says pop. So notice, by the way, at this point in time, after that for loop, top is currently has the value of 9, meaning index 9 is the top, which is true. We can see right here, this is the uppermost value in the stack. And so now we want to do what? It said that we want to pop 3 times. So we pop, and we pop. And I'm intentionally just scratching it off. And so now what is actually stored in top is going to be index 6, because 6 is at the top of the stack. And what does the last line of code say in this particular method? It says peek, which is also that operation called top. Top and peek are synonymous as methods or as operations. What it does is it returns the value at the top of the stack, but it does not actually remove it. So what's going to happen is what value gets returned right here? It's this value right here. Now notice the index and the value have the same number, which is 6. But don't make the mistake and say, oh, we're going to return what I just circled, because that's the index of where top is currently referencing. But we want to actually return the value at that index. And the value at that index is, again, right here. So we're going to return a 6, and it says to print it. And so that is our result. Kind of cool how stacks are actually working. Let's look at another one. What is the output of this one? So here, I'm going to start you off, and then I want you to actually draw this one out on a piece of paper. I'm going to ask you a couple of questions, and let's see if you get those correct. So here we have stack 1, we have stack 2, and now we have this for loop. Look at what that for loop is doing, and then pay attention to what's happening here in these 3 lines of code. We're going to be pushing into stack 2. What are we pushing into stack 2? The result of popping from stack 1. Kind of funky. Let's even back up very quickly. We made 2 stacks. They're called stack 1 and stack 2. I did this for loop. We looped 5 times. And what do? Is we pushed 5 values into stack 1. But stack 2 is still empty. So now we're going to actually push 3 values into stack 2. What are those 3 values? They all come from stack 1, and it's the result of popping stack 1. So stack 1 is now losing 3 values. It had 5. It's losing 3. And those 3 values it loses are being placed into stack 2. So now stack 2 has 3 values, and stack 1 has only 2 values. Finally, I want to peek the top of both of those stacks and return that result. So I'm going to trace through this, but I'm going to want to pause and even ask you to answer a couple of questions along that. Let's come over here to the tried and true tablet. Let's go. We have a for loop. What is going to happen in that for loop? The question I want you to ask yourself, after we execute that for loop, what is going to be stored inside stack 1 at the end of that for loop? And let's trace through that. The answer is we're going to be pushing these values: 0, 1, 2, 3, and 4, right? We push into that stack 5 times, starting at 0. So 0 goes first, then 1 goes on top, then 2 goes on top, and so on. Pretty straightforward. Cool. Now what happens is we need to push into stack 2. We're trying to perform that command. We want to push into stack 2 the result of popping stack 1. So the question would simply be, what value are we going to push right now into stack 2? And the answer is, well, let's pop off stack 1. And so we're going to actually scratch off the 4. And that 4 is going to get pushed into stack 2. And now we're going to be doing that next command, which is this. Bear with me. Erase all of that. And the next command is this one. We want to, again, push into stack 2 the result of popping from stack 1. And then we want to do it yet again. Then we want to do that command. So here's another question for you to consider. After doing both of those commands, what value will be at the top of stack 2. For clarity, after we do two commands, which two commands? These next two commands. We've already done the first one above. We've already done one push into stack 2. After we do these next two commands, what is going to be the topmost value of stack 2? And let's go trace through that. Well, after we do those two commands, let's do one at a time. We're going to pop off this 3. It's going to get pushed. Then we're going to pop off this 2, and it is going to get pushed into stack 2. It's that simple. So the topmost value currently in stack 2 is actually a 2. And finally, what does it say? It says we need to print two values. The first value, it says print stack1.peak. Make sure you can know the answer to that. What should get printed at this moment in time when I'm asking you to do this line of code? When we print stack1.peak, what should get printed? The answer is we're going to print 1, the value that is at the top of stack 1. And now when we do the next print command, which is print stack2.peak, it will of course print a 2. So that's how stacks are actually working, and it's helpful to actually go draw it out on a tablet. Let's look at one more of them, and we have here, we make two stacks. This one's funky. We're going to do what? We're going to push into that very first stack 100 times the values from 0 all the way to 99. So let's make sure I have this clear. I'm not going to draw out clearly a stack that huge, but we're going to push in from index 0 all the way to index 98 and index 99. We're going to be pushing the values of I. So 0, 1, 2, 3, 97, 98, 99. We perform all of those pushes. Now we have another for loop. We say we're going to loop here 99 times. And if I mod 4 is 0, we need to do what? We need to pop stack 1, and we need to push that result into stack 2. So we're going to loop from I equals 0 to 100, and whenever I is divisible by 4, so when I is 4, then 8, then 12, then 16, we need to do what? We need to pop from stack 1 and push it into stack 2, and then ultimately peek the top of those two stacks and print that result. I encourage you, trace through that one on your own, maybe even code it up. What really this amounts to is trying to figure out mathematically, wait, how many times is that? Is that 25 times, 24 times? Students get hung up on that. Not a problem. I'd say trace through it, draw it out, code it up, and you will get an answer. So what now remains is we want to look at our own implementation of stacks in Java. This can be done using static memory. This can be done using dynamic memory, meaning we can use an array or we can use a linked list. If we implement a stack as an array, that stack can actually become full. Now, as a linked list, this is much less likely to occur unless you just truly run out of memory. We're going to go over both of them. When we implement a stack as an array, what does this actually mean? This means when you look under the hood, when you actually examine the code for this stack data structure, you really just find an array. So then how is this array a stack, or what makes it become a stack? The answer is the behavior. Remember that definition of abstract data type? It's a data type that is defined based off of its behavior. So we're going to restrict, that's the key word here, restrict. We're going to restrict the behavior of the array, and we're going to make it behave like a stack. What does that mean? Well, an example, with an array, you can insert anywhere you want, right? You can insert at the front, index 0, you can insert at the end, you can insert at the middle, you can insert anywhere, right? But for the purposes of making this array behave like a stack, we will only allow insertion at the top. So we're going to have to define top. Do we want top to be index 0? Do we want top to be moving? We're going to define that. We're only going to allow insertion at the top, and that's where we're going to perform pushes. We're only going to allow deletion at the top. That's where we're going to perform our pops, right? So now we're basically transforming this array into a stack. How? By restricting how it performs, by restricting its behavior and only allowing insertions and deletions into the array at the top, wherever that top may be. What components do we actually need to store? Clearly, we need to store the actual elements themselves, but what else needs to get stored? We need to store the index of the top location, the way we drew that out on the tablet. We're going to assume the bottom of the stack is index 0. So that first element that actually gets pushed into the stack, it will get saved at index 0, and we're going to move up from there. We're also going to store the maximum size of the stack. Just call it max size. Now, you don't necessarily need to save that in Java. Other languages you might need to save this, such as the C language. But in Java, we can always identify what is the maximum size of the stack by just checking that array.length, whatever you've called that array, right? So that also gives you max size, or you can just explicitly save a variable called max size. So here's our stack array class. If you notice, it's just the data members, an integer array that I've called stack. I'm super creative. We have a variable called top, and then we have int max size. Clearly, max size represents the maximum number of items in the stack. How would we know if the stack ever becomes full? Meaning, if we had an array of size 10, from index 0 to index 9, if we have only one element, top is going to be pointing at index 0. But what if the stack is completely full? Top would be pointing to index 9, which is max size minus 1. Here's the constructor. We simply save size into max size. Of course, we need to actually create that array. So we're going to say stack equals new int of max size. And of course, we let top equal to minus 1. We don't set top equal to 0, right? Because if top is pointing to 0, that means we have a value at index 0. But right now, we're making our stack from scratch. There are no values, no objects, no data currently in that stack. So how can we indicate that it's empty? We set top equal to minus 1. And this is that explanation that I just gave. So boom, let's move on. Here are the methods: is empty, is full, push, and pop. We're going to implement each one of these methods. How do you know if a stack is empty? We just covered it. If top is ever equal to minus 1, that's how you know it's empty, right? So here is the code. Should look kind of familiar. How do you know if a list is empty? If head equals null. So what did we say? We said public boolean is empty, return head equal null. How do you check if the stack is empty? Return top equal minus 1. If top equals minus 1, this will return true, else it will return false. As we've covered, you could write this as a branching, as a selection operation. If top equal minus 1, return true, else return false. Nothing wrong with that. That has a good level of clarity for software engineering. However, this is also quicker. It's just a simple, straightforward Boolean expression. What about is full? How would you write a method to check if it is actually full, remembering that maximum size is the maximum number of elements in the stack? So item 1 goes at index 0. If the stack is full, the top will be at index max size minus 1. Here's the code. Public boolean is full, return top equal max size minus 1. Pushing. How does a push work? We want to add it to the next available position. We can only push if the stack is not full. So first we need to check, make sure we have room. If there is room to push, if the stack is not full, we will push it. Otherwise, if there's not room, we need to present an error message or perhaps throw an exception. So here is the code. Look at what happens. Kind of cool. You don't need to code it like this in one line. But check out what happens. We're saying take this value, as long as it's not full, we want to go ahead and add this value at the next position. So what did we do? We said take this new value and save it into the array at what index? At index, and check this out, plus top. Now, I didn't have to do it that way. I could have done it slightly different. Come over here to the tablet. I could have said top plus plus. Thereby, I've now updated the value of top. If top was previously 4, now we've made top 5 the next position, and then we could simply take the value and save it at the new top that we just updated. That would work just fine. Or you can see here, we really just did that in one step. We said, take top, let's first increment top. Remember, that's pre-increment in Java. We first increment top, and then we save the value into that next position. So this works perfectly fine, one line of code. What about popping? We can only pop if the stack is not empty, if there's at least one element available. So if the stack is empty, we print an error message. Otherwise, we need to now pop off that element. Well, in order, after we pop off that element, we also need to reduce top, right? Because top needs to now go down one index to indicate that a value has been removed. So you need to return the value at top, but we also need to decrement top. You could do that in multiple lines of code, or you could really just do it as you see here. Check this out. I'm saying return stack at index top, which is correct. You really just want to remove, you want to return the value at the top, but you also want to decrement top. So so what's happening here is I'm returning the value at top, but then check it out. I'm saying, well, after you return it, do a post decrement. Decrement top afterwards. If we did not do it in this fashion, you'd have to really have 3 lines of code. You'd have to first take the value at the top, save it into a temporary variable, then you'd have to decrement top, and then you'd have to return that temporary variable. Nothing wrong with that. It's very clear. Or you can just say, you know what, let's return stack at index top, and then do a post decrement where we're now reducing the value of top so it points to that next value. And also top peek, pretty straightforward method. This top method or top operation, which is like peek, we're just going to look at that top value in the stack, but we're not actually going to return it. And here is that code. Just return stack at index top. So this is just small snippets of the code, but that's really it. But if you would like to see the entire code, it's available on GitHub. It's in the description. Click on that link, look around with it, play with it some. It's all available to you. Takes years of mastering Photoshop. I get it. Okay. Not that funny. I don't know. I need some better fail pictures. I love the next one though. The next one's fantastic. Me, my friend with no other choice, giving them my crappy code. We have all maybe I've been on the receiving end of that, or maybe on the giving end. Who knows? We would like to now talk about the implementation of stacks in Java using linked lists. So we can also implement these as a linked list. The advantage is now we have no fixed size, and we can use dynamic memory and take advantage of those things. But once again, what does this mean? This means when you examine the code of a stack or a linked list version of a stack, when we look under the hood, what we're going to find, instead of an array, we're going to find an actual linked list. So once again, how then is that linked list a stack, or how is it transformed into a stack? And the answer is the behavior. We're going to restrict the behavior of the linked list and limit how we can actually work with that linked list, or what actions can be performed on that linked list, thus making that linked list behave like a stack. The example, with a linked list, you can insert anywhere, right? We can insert at the front, we can insert at the back, we can delete anywhere. At the same time, but to make it now behave like a stack, we're only going to allow insertion where? At the top, which we're going to have to define. What is the top? We're only going to be allowing insertion at the top to take care of pushes. We're only going to allow deletion at the top to take care of those pops. But once we do that, by basically putting handcuffs and restricting the operations of a linked list, we've effectively transformed that linked list into a stack. So we're going to use a basic linked list, but we're going to limit its functionality, thus getting our behavior of a stack. And in fact, the linked list implementation of a stack is actually just a very easy linked list. Perhaps you recall when we covered insertion on linked lists, the day we taught insertion, that I said that we're going to have a goal of inserting anywhere in this list in its correct position. But I said, but first, baby steps. Let's first try inserting at the front of the linked list. Then let's try, as baby step number 2, to insert only at the end of the list. And then we do the huge, fully comprehensive insertion method where we insert anywhere based off of its sorted order. What was baby step 1? Inserting at the front of the linked list. And it was such a super easy method. Well, guess what? That's what a push is when we're pushing into a linked list version of a stack. We're really just inserting at the front of that linked list. So step 1 here says, choose the location of top. Where should top be? What is the actual best choice? Top could be at the front, or we could choose top to be the end of the list. Which is better? Which is going to be faster? If you allow top, which is going to be a variable like head, it's going to be a variable that always has access to wherever the top is going to be. Do you want top to be at the front of the list, or do you want top to be the end? Which is going to be faster? And the answer should hopefully be clear. If we choose top to be the end, every single push and pop will require a traversal. That would be a disaster. Versus if we allow top to strictly be at the front of the list, every push and pop is O of 1, constant time. So the best choice, we let the top be the front of our list. Therefore, a push is simply inserting into the front of a linked list. That's the easiest type of insertion. Super cool. We're only going to be changing 2 references, just like we changed those 2 references when we inserted at the front of our linked list. A pop would simply be deleting that first node. Well, how do you delete the first node? If you have head pointing to the first node and you want to delete it, what do? You take the address of that second node and you save it into head. So head equals head.next. How easy is that? That's now deleting that first node. But instead of using the variable head, we have the variable top. Top equals top.next. Done. We deleted that first node. Super straightforward, one of the easiest types of deletions. So I say here, in fact, the linked list version of a stack is the easier to code than just a traditional linked list. I would even argue easier to code than an array-based version of a stack. Every node will be an element of that stack. Each node has a data value. Each node has a next. It's really just a linked list, right? And we're going to simply push at the front of the list. We're going to pop from the front of the list. So we have these 2 classes, just like we had 2 classes for linked list. We have stack node, which is like LL node, and we have stackll.java, which is just like linked list.java. We're going to use the same methods. You're going to have the same isEmpty. You can have the same push and pop. You're going to have maybe a print list if you wanted to print the contents of the stack. But again, we're restricting the functionality. No longer can we insert anywhere into our linked list, but instead we're only inserting at the head, at the top or the front of this list, and we can only delete from that front. Here is your stacknode.java class. It should look like the LL node. You got a data, you got a next. Instead of being called LL node, it's called stack node. Here's your constructors as we have previously seen. Here are the getters and the setters, the accessors and mutators. Here is the stackll.java, which is like linkedlist.java. Instead of a variable called head, we now have a variable called top. Pretty straightforward, right? At the beginning, when we make a new linked list stack, top is going to be null, indicating we haven't actually inserted or pushed any items into the stack yet. And what remains are we now have many methods. We have isEmpty. How would you check if the stack is empty? Well, it's a linked list. How do you check if the linked list is empty? If head is null. If top is null, it's empty. Here's your code. Return top equal null. Boom. Easy. You should immediately understand that. We've seen that method for linked lists for too long. What about a push method? What if we want to call this public void push method? and we want to actually push this data value into the stack. But what's really going to happen is we want to call the real push method, like the real insert method of a linked list. So we're going to call the real push method, which is going to be private. We're going to send over the data value, and we're going to send over the top of the stack currently, and we want to push. Here's the code. Notice we make a new node. I could have done this in one line of code, but I chose to do it in 2 lines to make it clear. We make 1 line of code here where we make a new stack node with the data value, and this new node is going to be the new first node. So it has to point to the previous first node. So the next to this new node, what do we put there? We put the address that is in top, which is the address of the previous first node. So this new node is pointing to the previous first node. We then take the address of this new node and we save it into top. And then, so now top points to this new node and we return top, and it gets saved right here when it returns back into the actual top data number. The pop method, check this one out. The pop method, we need to actually pop off of our stack of value, return that value. So I'm going to show you here, we have the public and here we have the private. Let's first look at the public. The public says, hey, let's take the node that is at top. So top is just an address, right? It's the address of a node. Let's take the address of that node and save it into temp. So now we're temporarily saving that. I then say, let's call the real pop method. And this is overkill. You could have just really made one method here. But let's call the real pop method with top, and then we return temp. But all the real pop method, the private method, does is it simply says top equals top dot get next. We're simply making top point to the second node. Top was pointing to the first node. Top equals top dot get next. It now points to that second node. And we have skipped that first node. That first node, if nothing else is pointing to it, the Java garbage collector would immediately erase it. No mercy, no hesitation. Top equals top dot get next, and then we return top. So you might be thinking, wait, did we just delete that first node? No, because if you come back and you look at that public method, what we did here is we first saved the address of top into temp. We called the private method, so we never lost access to that first node, even though top no longer points to it. Top points to the second node, but we first saved it into temp, that first node, and now we can return the address of that first node. What is the top method? It just really returns the value at the top. Pretty straightforward. Here, I assumed that maybe that top is just returning an integer. You could return the access to the entire node. You could return parts of it. Here, we're just returning an int value. And this is the private version, which says return top.getData. It gets saved into top value, which then gets returned. All of that code is available at GitHub. That was gone over quickly. I see I'm at 43 minutes. That's more than long enough for the video. Anything you want to hear again, rewind. Listen again, ask questions, leave a comment. Was that splendid? I don't know. Delusions. There's no greater joy than soaring high on the wings of your dreams, except maybe the joy of watching a dreamer who has nowhere to land but the ocean. Oh, of reality. That hurts. No. Sorry for the pain. It's been fun. As always, reach out, leave comments. Take care, everyone.